What do submarines have in common with this? Well, today we're going to answer that question and explore Cartesian divers. The Cartesian diver is a classic science experiment that demonstrates how an object that ordinarily floats can sink when under pressure. Named after René Descartes, the Cartesian diver has been around for over 400 years. Itinerant glassworkers, who were a type of traveling entertainers, commonly included Cartesian divers as part of their demonstration. However, rather than explaining the scientific principles behind how it worked, itinerant glassworkers tended to advertise the experiment as a magic trick, where divers could move telekinetically. While itinerant performers declined in popularity in the 1900s, the Cartesian diver experiment can still be done today with simple household materials. Today, we are going to perform two versions.
For the first version, create your Cartesian diver by taking a pipette and cutting it about an inch from the bottom of the bowl. Next, place and secure a hex nut onto the skinny part of the pipette. This will act as a weight to ensure that the diver stays upright. Now squeeze water into the pipette and test that the diver barely floats, aka it should be nearly neutrally buoyant. Then, place the diver into a large bottle that's fully filled and screw on the top. Currently, the diver floats. However, when we squeeze the bottle, the diver sinks. When we let go, the diver rises once again. Let's see it again in action. Now in our second version, we are going to use a ketchup packet instead of the pipette. After making sure it barely floats, we can follow the same procedure as the pipette diver. As you can see, we get the same results. This begs the question, what is causing this phenomenon?
Density is the mass per unit of volume. In other words, how heavy something is in comparison to its size and shape. An object floats when its average density is less than the fluid that surrounds it. In our experiment, the pipette and the ketchup packet both originally floated because of their air pockets. Air is less dense than water, and this contributes to the average densities of the divers being less than the density of the water. Therefore, the divers float. When the bottle is squeezed, the pressure within the bottle and within the divers is increased. Focusing on the air pockets within the divers, we can use Boyle's law, which states that at a constant temperature, the volume of a gas is inversely proportional to pressure, aka if pressure increases, volume decreases, and vice versa. Therefore, in our experiment, to account for an increased pressure caused by squeezing the bottle, the volume of the air pockets within the divers decrease and the density of the divers change.
Looking closely at the pipette example, you can see that the water level inside the pipette slightly rises. Following Boyle's law, the volume of the air pocket decreases. But note, as a whole, the volume of the pipette stays the same. The only difference is that it has more water inside of it. Thus, the increased water content increased the diver's mass. Consequently, the average density of the diver increases until it is greater than the density of water, where at that point, the diver sinks. Similarly, with the ketchup packet, the air pocket also shrinks by Boyle's law. Because the packet is completely sealed, the packet is compressed and the volume of the diver decreases. All the air and sauce are still in the packet, so the mass of the diver still stays the same. However, just how the water level barely rose in the pipette example, the change in volume is very tiny, and it looks like nothing happened from the outside. This scenario also increases the average density of the diver until the diver sinks.
Now, back to our original question. How are these huge technologically complex submarines related to a bottle of water with a pipette or a ketchup packet inside it? Well, both instances utilize the same principles of buoyancy and pressure. Submarines are built with ballast tanks that fill with water or air depending on if the submarine is going to sink or resurface. The interchanging between air and water is manipulated to control the submarine's buoyancy. When the ballast tanks are filled with air, the submarine is less dense than the water surrounding it, causing the submarine to float. On the contrary, when the submarine prepares to go underwater, the ballast tanks will open up to let in the water. In doing so, the volume of the air pockets within the tanks decreases, while the submarine's ballast tanks are becoming more dense than the water. Simultaneously, the pressure of the submarine will increase as it goes deeper into the ocean. In the end, the submarine ends up sinking. In our Cartesian diver experiment, the pipette represents a submarine with its ballast tanks. As we explained earlier, the bottle is squeezed and the pressure is put on the pipette, making the water level inside it rise. The pipette would sink just as how a submarine would when the water level and pressure in its ballast tanks increases.